volume, newtons. Actually, I'm going to put newtons over here. For force, kelvins for temperature, okay? Calories is another measure of energy. Coulombs is a measure of charge. Okay? Anything else? Pounds and pints. All right, pints is another volume one. And I heard pounds. Pounds goes up here under force. Anything more? It's a pretty good list. So I've started compiling some of them here, and I separated out newtons for a very specific reason. And I'm actually going to pick a few others from this list that I'm going to move over. So we've got distance, energy, current, time, brightness, resistance, mass, power, volume, temperature, charge. These all have one thing in common. And the thing that they have in common is that they are all directionless. None of them have a specific direction. You may be saying, well, wait, what distance is at the top? Yep, we're going to get to that in just a second. So these are all what we call scalar units. They're all units that have no direction, or have a magnitude but no direction. Have magnitude but no direction. All right, so that's a pretty comprehensive list of basically everything we're going to talk about this year, except for, I think I don't see anything on waves here, but otherwise it's pretty good. Over here on the other column, we're going to have vector units. Vector units differ from scalar in that they have direction, and they only operate in straight lines. So have magnitude and direction. All right. All right, so our basic units that we're going to be talking about for motion. Displacement and direction, or displacement and distance. Distance is the total path traveled, whereas displacement is simply a change in position. Distance, total path traveled. Whereas displacement is a change in position. Or if you want to consider distance as the crow flies. Okay. So, if I were to start by standing here, and I walked, let's say this is 2 meters here, and 2 meters here, and 2 meters here, what would be the distance I've traveled? 6, if you were counting with me, because it was 2 and 2 and 2, 6. But what would be the displacement? 2, because my 2 to the east has been countered by my 2 to the west. I could consider 1 to be positive, 1 to be negative in an arbitrary set of coordinates that we can set up. Okay, let's go further. 1, 2 meters here, 1, 2 meters here. Total distance traveled and displacement, 2. And I'm here, displacement, 0. So understanding that if our original position returns to, or we return to our original position, displacement is 0. It can be a little bit strange to think about that, simply because that implies that even though you traveled, you haven't gone anywhere, and that we would actually measure that as a 0 vector. Okay? So displacement, distance, and the difference between the two. Next one we're going to tag in here is simply time. So I occasionally have had a discussion on whether time is a scalar or vector concept. that is an awful discussion. We're not going to have it. It hurts my head. Time is a scalar value. It moves forward, end statement. We will talk about the fact that it moves forward at different rates in February, but we will not talk about it going backwards because it has never been done and is, to our understanding, not possible. Therefore, time is a scalar unit. All right? So time, we're just going to label that as measured in seconds. And for those of you who are feeling like adding something to it, you can also indicate that it is influenced by gravity. And that'll be a teaser for February. All right, measuring motion. Now we're going to get to the ones that you guys started talking about for the daily question, and that's speed and velocity. Speed is simply a rate of change, or the amount of distance traveled in a set amount of time. Amount of distance traveled per unit time. Whereas velocity is a rate of change in position over time. Rate of change in position over time. Now, the notable difference here is that we can recognize velocity as a vector unit because it is talking about changing position. And we know changing position in displacement, if that value maintains 0, then even if we walk in a circle, our average velocity would be 0, whereas our average speed would be a very different value. You would have to deal with how fast you're actually walking in the circle. Makes sense? Okay, so we're going to go ahead and relay these in terms of graphing motion. And I'm just going to set up a coordinate axis here. We're going to call this 0, 1, 2, 3, 4, 5, 1, 2, 3, and we're going to try this. I'm going to ask you to move just around for a second. All right, so I'm going to start here, and I'm going to call this position 0. Okay, so 0 on our coordinate axis. If I take a set amount of time to walk forward, set amount of time to walk backwards, we can track where my position is at any point in time on distance versus time graph, or a displacement versus time graph, I suppose I should say. So let's say I take 1, 2 seconds, 1, another 2 seconds, 1, another 2 seconds. I'm going to stand here for 3 seconds, 2, 3. I'm going to walk back 1, 2, 1, 2, 1, 2, 1, 2, and I'm going to stop here. I was counting seconds rather than 6. Okay? So if I want to actually graph out what I just did, I'm going to start here at 0, and what am I going to do? This is time, this is displacement. What am I going to show? A sine curve. So something kind of like that. Other thoughts? What am I going to do? How am I going to show it? All right, go up, stay steady for 3 seconds, and then go back until a negative. Okay? Others? Carter, I see you saying he's dead. Oh, you're right. I did mix up my axes. Thank you. And that's actually a really important point because time should always be on the x-axis. Sorry, thank you. So our conversation we were having here just a second ago, you were saying you liked Brennan's, correct? You like Brennan's?
Yeah, I forgot that you stayed there.
Okay, forgot that I stayed here. Any other reasons? Okay, so my velocity was constant. So the sine curve of the original suggestion indicates that I was accelerating and slowing down, stopped only for a brief instant, accelerating, speeding up, slowing down, stopping for only a brief instant. When in fact what I tried to model was walking at a constant velocity, stopping for a set amount of time, walking at a constant velocity back in the other direction. Okay? We can actually see how this represents vector units by looking at the fact that this is a positive change in position and this is a negative change in position. So if we want to count towards my desk at the negative end of the axis and towards the back wall as the positive end, we can then actually even find velocities based on these. So it took me, 6 seconds to get to the back wall? Graph not drawn to scale. 1, 2, 3, 4, 5, 6. And then I stayed there for 3 seconds. 2, 1, 2, 3. And then I really not drawn to scale. 1, 2, 3, 4, 5, 6 to get to there. 7, 8 to get to there. Not to scale. Wow, that's really bad. All right. Math teachers would probably hate me for that. All right, so I can pick out a couple of different details here. Anytime I've got a displacement versus time graph, I can easily find total displacement. That's easy. I just look and compare where am I here versus where am I there. So if I wanted to measure my displacement between these 2 points, I could say there was 1, 2, 3 yellow tiles. Easy enough. If I wanted to find my displacement from here to here, I would say it's -1 yellow tile. Note I said the negative there. In physics, negative simply shows direction. It has no other bearing other than that. Okay? I can also, however, find velocity and speed. I can find velocity by looking at each segment and recognizing that velocity is a rate of change in position over time. My position changed by 3 yellow tiles over 6 seconds. So 3 over 6, I have 0.5 yellow tiles per second, which roughly equates to, I imagine, about a meter a second. Okay? Then if I look at this position, what's my velocity going to be here? Say again? Right, same thing but negative, noting that I'm going the opposite direction. So negative 0.5 yellow tiles per second. Okay? So not only can I find displacement, but I can also find velocity from this. Simply by finding slope. Okay, that should be actually pretty easy to recognize because slope, m, equals change in y over change in x, right? Well, in this case, change in y is change in displacement or change in position over change in x, which is change in time. Therefore, we get our first equation of the physics year, velocity, which we define as a rate of change in position over time, can be calculated as change in position over change in time. Okay? Easy enough? Okay, let's take this and go another step. Where are my calculus students in the room? So last year at the end of the year, you guys took pre-calc then, yes? Oh, so some of you have already taken calc. All right then. Well, so you should be pretty easily be recognizing these as derivatives of each other. Derivatives? Yes, derivatives at this point. While we won't actually use calculus in this class, I will make connections between this and that math, simply because Newton invented calculus to describe physics. So it'd almost be a disservice to Newton to not mention that, hey, this math out there that exists, this is why it exists. We won't use it, but we'll talk a little bit about it. Okay? So velocity, change in displacement over change in time, you can recognize that it's the derivative of the position function. For those of you who have not taken calculus, you can recognize that the slope of a displacement function is velocity. Good? Okay. Going up one step. So graphing motion, now we're going to actually graph velocity. Okay. So the first segment of my motion graph, we showed a constant velocity of 0.5 yellow tiles per second. So if I'm going to mark this as 0, and we're going to put time on the x-axis because that's where it belongs. It is the independent variable. And I'm going to put velocity on my y-axis. I'm going to show a constant velocity for 6 seconds. What should my graph look like next? Velocity should go to 0. So I'm going to draw it down here. It's going to sit at 0 for how long? 3 seconds. So about, I think I'm drawing this a little bit better to scale. About to there. All right, now what? Does it? Goes down. Where does it go to? Negative 0.5 yellow tiles per second. So right about here. And how long does it sit there? 8 seconds. Excellent. So that was from 9. So this should go to right about 17. Math teachers would probably be a little less mad at me. There's a little bit more to scale. Yes? They'd probably have some issues with my intermittent labeling of the axes. All right. So that was a catch that we wanted to make sure that people recognized, was when we went in the opposite direction, my velocity versus time graph actually shows a negative value, agreeing with what we calculated from the slope earlier. Okay? Calculus students, if I wanted to know how far I'd traveled, how could I find it based off this graph? All right, I could integrate my value here, or for non-calculus students, I just find the area under the curve. So if I want to know how far I'd gone, I'd multiply 0.5 yellow tiles per second by 6 seconds, and I'd show I went 3 yellow tiles. So area under a curve is displacement. Okay? Calculus students, you could also talk about integrating the velocity function. Okay. All right. So changing between displacement to velocity, all we've done is we've instead graphed the slope of the position function to find our velocity function. We can actually take this a step further, but to do that, I'm going to try a new one where I'm going to not walk at constant velocities, because I want to be able to show the next kind of fast that we described. We want to be able to talk about acceleration. Oh, no. I mean, it's not a far step, but it's an unnecessary one for this level. You could talk about it can be fast, that's true. All right, so starting from my 0 position, I'm going to take very amounts of time to get to each one of these. And what we're going to do then is we're going to graph it on a position, a velocity, and an acceleration graph. Okay? So we're going to see if we can do this. 3 seconds, 2 seconds, We'll pretend that was 1 second. 1 second, 2 seconds, 3 seconds. So seeing if I can physically do this. 3 seconds, 2 seconds, 1 second, 1 second, 2 seconds, 3 seconds. Even if I didn't quite illustrate it, get the idea. Okay? So, position versus time. We have position here, or displacement, time, and we're going to have 1, 2, 3 yellow tiles. Okay? What's this one going to look like? What is this graph's overall shape going to look like? Like a parabola, absolutely. So we're going to go up to here. Keep going up. Actually, I drew that. I actually did that really weirdly. I did it backwards. Let me try that again. That's why it was so hard to do. All right. Yeah, fast first. So 1 second, 2 seconds, 3 seconds, 3 seconds, 2 seconds, 1 second. That's way easier to do. That's why it was so hard to do the first time. Yeah. It's a Tuesday. All right. So this graph would then represent the motion that I just illustrated as I'm accelerating towards the, or decelerating towards the top and accelerating towards the bottom. So a little bit better of a parabola. And we would represent this as 1 second to here, 2 to there. It's a little better, not great. But we get the idea, yes? If your answer to that question is no, you should say it so I can try again. Not the demonstrating thing, that's going to be abysmal. Yeah, no. Okay, so position versus time. In this case, what we'd then be looking at, yeah. So, yep, to here, 1 second. This point would be at 3 seconds. This point would be at 6 seconds. This point would then be at 9. Somewhere, this should taper off a little further. Somewhere about here should be 11. It should be symmetrical, but I am possibly the worst artist in the room. Competition, all right. You have no idea. All right, so Ziga, does that help? So we had 1 second, 3 seconds, 6 seconds, 9 seconds, 11 seconds, 12 seconds. So it should take about 12 for the whole pattern. And at 6, you should be at the top. But noting that these are not divided into equal segments. Good? Okay. All right. So from this, we could then start talking about velocity and slope and, well, our velocity versus time graph. So our velocity versus time. As we go from this starting point to our 6 second mark, what is happening to the slope? It's slowly decreasing. Okay, so in turn, what is happening to the velocity? It's slowly decreasing. Now, if I was actually able to draw this well, it would look very nice and parabolic. So I'm just going to note this is parabolic. Okay. And here I'm going to have velocity. Here I'm going to have time. And in this case, I'm going to start at a high positive velocity because the highest slope I should have is right here. Even if my drawing doesn't represent that well, I know that this slope at the top has to be what? 0. Why do I know that slope has to be 0? Okay, I've got a few reasons. I changed direction, I stopped, I turned around. We know it's a parabola, and at the top of a parabola, the slope is 0. Okay, so various reasons, I know that spot's going to be 0. So I'm going to mark that one here. I know this is my highest velocity, and this is my greatest negative velocity. So in this case, I'm going to be able to draw, my dot's there, a straight line showing the change in velocity. Okay, so went from positive to negative. Now I do want to note here that during this entire situation, this is a positive velocity, meaning that through the entire segment, we're moving towards the back wall. Down here we have a negative velocity, meaning that during this entire segment, we're coming back towards the front of the room. Excuse me. All right, so we'd mentioned that from a displacement versus time graph, we can use the slope to find velocity. Well, the same thing works here. On a velocity versus time graph, we can use the slope to find the next function, acceleration. Calculus students, how would I do it? How would I go from this to acceleration? Derivative, yeah, I just take the derivative. Non-calculus students, all I've got to do to go from velocity versus time graph to finding acceleration is find the rate of change in velocity. So there's our definition for acceleration. A rate of change in velocity. Okay, so my rate of change in velocity is acceleration, then the function I'm looking for off of velocity versus time graph is simply the slope. So the slope of a position versus time gives me velocity. The slope of a velocity versus time gives me acceleration. So slope is acceleration. And we can show that as m is equal to change in y over change in x. Change in y is going to be change in velocity over change in time. And we have our second equation of the year, acceleration. Okay. Now, I'm going to try a few more of these, but we're not going to actually, well, we'll toss in this last graph real quick. So acceleration versus time. What's my acceleration versus time graph going to look like for this function? Horizontal line where? Negative. The slope of the line is negative the whole time, so that means it's horizontal in the negative function, or as negative value the entire time. Wait a minute. But I started out going in that direction, and I ended coming this way. How can the acceleration be the same the whole time? Say that first part again. My velocity was constantly decreasing or becoming more negative. So just because an acceleration is negative doesn't mean I'm slowing down. It doesn't necessarily mean I'm speeding up. The comparison between the velocity at a specific point in time and the acceleration determines if we are slowing down or speeding up. So, okay, let's see if I can do this. I want to know positive velocity, positive acceleration, negative acceleration. We're going to keep that direction as positive. We're going to keep that direction as negative. So if I start here, and I'm going this way, what do I have in terms of those concepts? Positive for both. Okay, good. Now going back this way. Are we sure? What was the velocity, positive or negative? Negative. We can agree on that. I was going that way. What happened to me as I was moving? I slowed down. So what should the acceleration be? Positive acceleration because it shows a conflict between the velocity and the acceleration. When the velocity and the acceleration disagree in their sign, then I wind up slowing down. When they agree in their sign, I begin speeding up. So continuing with another example, what's it going to be? Both negative. Because I'm going in the negative direction, so velocity has to be negative. And I was speeding up, so the acceleration must have the same sign as the velocity, meaning both would be negative. Okay, one more. Let's see if I get it right. Okay, good. Positive velocity, I'm going that way, we said that was positive. Negative acceleration because I was slowing down. I was accelerating the opposite direction as my velocity. This is something that we can see very easily anytime you throw an object. Anytime you throw an object, you're instituting a velocity to it at the beginning, but once it leaves your hand, it always has the same acceleration. Its acceleration's always down. Gravity, right? At least I hope so. So if the acceleration is always the same, then we should notice the exact same kind of trend as when I walked correctly towards the back, slowing down, stopped, walked back towards the middle, speeding up. So when you throw an object into the air, it's moving fastest right as it leaves your hand and begins slowing down until it stops, meaning that it had a positive velocity and a negative acceleration, showing that it's slowing down because they're opposites. And then once it reaches the top, it begins accelerating in the negative direction, so its velocity and its acceleration are in the same direction, showing it speeds up. And that's our last piece, is if velocity and acceleration have the same sign, objects speed up. And conversely, if they have opposite signs, they slow down.